Example 11.3, finding a specific heat. A 125 gram block of an unknown substance with a temperature of 90 degrees Celsius is placed in a styrofoam cup. And I think for our purposes, we're assuming that the styrofoam provides perfect insulation, which means that no heat is escaping out of the styrofoam. So the styrofoam, or into, placed in a styrofoam cup containing 0.326 kilograms of water at 20 degrees Celsius. The system reaches an equilibrium with a temperature of 22.4 degrees Celsius. So what is the specific heat of the unknown substance if the heat capacity of the cup is neglected? So by neglecting the heat capacity of the cup, we would be assuming either the amount of mass that is affected is close to zero, or the specific heat is very low, or that the change in temperature of the cup is very low. And I think this works out in practice, but what turns out to be the lowest of those is the mass, basically because the temperature doesn't reach very far into the walls of the styrofoam, and so it affects very little of the mass. Now there's a couple of ways we could do this problem. One is that the sum of the energies initial equals the sum of energy final, or we could do it the way they suggest, that the heat of the cold, Q cold, equals negative Q hot. And how do they describe Q cold and Q hot? Well, the water starts at 20 degrees while the mystery material starts at 90 degrees. So they're saying the heat gain of the water is equal to negative of the heat gain of the material. Let's actually change these subscripts around a little bit. We'll call this one M water, C water, T water initial, and T water final. This will be mass of material, C material, T material zero initial, and T material final. And so the heat gain of the water would be mass of the water times C of the water times T water final minus T water initial. And the heat gain of the material would be mass of the material, C of the material, times T material final minus T material initial. And I want to put a negative sign in there, or, yeah, so let's erase that and put in equals and a negative sign. On the other hand, this version of the equation puts all of the final things on one side and all of the initial things on the other. So if when things start to get ugly in terms of writing out terms, I like to write things in a more convenient term, which is through a multiplication, matrix multiplication, which would be mass water, C water, and mass, what's the other one? Mass of the material, C material times T initial, T water initial, T mass initial equals, and then that same matrix times T water final and T mass, or T mystery final. Sorry, it didn't fit where I wanted it to. But you can see why this one will be more convenient right off the bat for solving for specific heat of the mass. I'm replacing the TW final T minus TW initial with just a straight delta TW, and replacing TM final minus TM initial and the negative sign with a negative change in T of the material. You can see that the water has gone from 20 to 22.4 degrees, and so its change in temperature is 2.4 degrees, while the mystery material has gone down from 90 to 22.4 degrees, which is a change of negative 67.6. But since I put this negative sign here, it's positive 67.6. And plugged in the mass, the specific heat of water, and the mass of the mystery, the mass of water, and the mass of the mystery object. And the answer comes out to be 386.4 joules per kilogram degrees Celsius. You could also say, instead of degrees Celsius down here, Kelvin, since they both have the same, since they both represent the same change in temperature. So if you look here in table 11.1 at copper, it has a specific heat of 387 joules per kilogram degrees Celsius. 387 is very close to 386.4. So in their remarks, they say, comparing our results to the values given in table 11.1, the unknown substance is probably copper. Note that because the factor of the change in temperature of the water had only two significant figures, the final answer must similarly be rounded to two figures as indicated. So whereas I rounded it to 386.4, I should have rounded it based on principles of our degree of accuracy of measurement. Should have been measured to 390. 3.9 times 10 to the second joules per kilogram Kelvin. Question 11.3. Objects A, B, and C are at different temperatures, A lowest and C highest. The three objects are put in thermal contact with each other simultaneously. Without doing a calculation, is it possible to determine whether object B will gain or lose thermal energy? No. And I think this is where the other form of the equation would shine, that the sum E initial equals sum E final would be a good use. The heat energy in this would count all the heat energy in all three objects, and this would also contain the heat energy on all objects. And you would not just have the heat of the cold object going up and the heat of the hot object going down. You would need because you wouldn't know whether the middle object should be considered to be cold or hot unless you knew the initial temperature of the cold object, of the middle object, and its final temperature, in which case you would know whether it was cold or hot. It would depend on what you knew. We will shortly be doing an example 11.4 where we will just be using a heat transfer of the water, aluminum, and glass. So we will come into that situation fairly shortly. But meanwhile, exercise 11.3 says a 255 gram block of gold at 85 degrees Celsius is immersed in 155 grams of water at 25 degrees Celsius. Find the equilibrium temperature, assuming the system is isolated and the heat capacity of the cup can be neglected. And once again, it's a combination of a couple of things. The amount of mass of the cup is very, very small because of the insulation. And the specific heat of styrofoam is actually somewhere close to the specific heat of air. Anyway, you should eventually have the specific heat of water memorized, even though 4,186 joules per kilogram Kelvin. Okay, yeah, it is. Look at this orange line here. That's the isobaric heat capacity of water. So isobaric means we're just going to keep the pressure at 1 atmosphere, 101,300 pascals. And you see it stays right there at 4,186 joules or 4.186 kilojoules per kilogram Kelvin. So yeah, it's a very straight line across from 0 degrees Celsius to 100 degrees Celsius where it would boil. So that means if you memorize the 4,186 joules, C specific heat of water is 4,186 joules per kilogram Kelvin, you're going to be correct for any situation at least where we're at atmospheric pressure, which is essentially any place on the surface of the Earth. So the other thing we need here is the specific heat of gold, which is a mere 129 joules per kilogram per degree Celsius. So I will write that under gold, 129 joules per kilogram degrees Celsius. And you know how I'm going to do this different this time? I wrote out a huge big equation last time with all not plugging in anything until the end. But what I'm going to do first here is I'm going to find out what is the heat of the water. How much did the water get heated? And that's going to be mc delta T of the water, which is 0.155 times 4,186 times, oh, I can't do that. Dang it. I actually should have done it in the first part because we did have sufficient amount of information to find the actual change in heat or the actual heat exchange. Okay, so I'm basically going to treat it as mc delta T equals mc delta T, except one of these has a minus sign on it. The delta T here, T water initial minus T water final, is the negative delta T. And I'm seeing that this actually still is more easily approachable with E initial equals E final, because we could find the final energy in this with M MC MC and T final equals the MC of gold, MC of water times T initial of gold, T initial water. Let's do it this way because I think this is going to come out nicer. The left-hand side with MC times T initial is going to be 0.255 times 129, and then we'll use the same thing with water, 0.155 times C is 4,186, and that will be our first coefficients, and then the T initials are 85 degrees, and the other one is 25 degrees. And then over here we get the same numbers. 0.255 times 129 is 32.9, and 0.155 times 4,186. And here, both of the T finals are going to be the same. Now the 32.9 times 85 plus the 649 times the 25 gives you 9,021. And the 32.9 T final plus 649 T final gives you 681 T final. And you come up with a 27.9 degrees Celsius. I, th I think I'm going to come back to this problem in a little bit. After I do example 4, I'm going to work it the same way I just did with a matrix form. And then I'm going to have a look at what they did using constructing a data table. And then I'll compare those two ways. And after I've kind of compared those two ways, I'll try to come back to this example and see what it would look like if I had constructed a data table to solve it instead of doing it with matrices.